Quantum mechanics is notorious not only for the difficulty in understanding it, but because of its strangeness as well. The double-slit experiment ultimately shows that our reality is not made of physical stuff, but of information. Its results, and those of other which-way path experiments, deal a fatal blow to materialism. The double-slit experiment is based on the wave-particle duality of subatomic particles. As simple a concept as it is, it produces some of the most astounding experimental results of quantum mechanics. This experiment stands at the heart of quantum weirdness because it produces the strangest results in science. The original double-slit experiment used photons of light, but later versions used electrons, but the results are the same. The double-slit experiment is responsible for starting quantum physics. Shooting classical particles, that is, small balls of matter at a screen, with a single slit in it, produces a simple spray of particles on the second screen behind it. When a wave passes through a single slit, it produces a similar pattern, that of a bright spot in the center that dims as one moves away from the center. A wave of water passing through a single slit is a good example of this effect in action. When you add a second slit, the classical particles would tend to form two sprays of particles on the second screen. This is the pattern made by bullets shot from a gun at a sheet of steel that they cannot penetrate with two slits in it. When a wave passes through a double slit, it produces the bright and dark striped pattern seen here. This pattern results from the interference of the two waves produced by the slits. This effect can be seen in a wave of water that passes through a double slit. Here's an illustration showing the particle pattern and wave pattern together. The difference is striking and obvious. Shooting subatomic particles at a screen with a single slit in it produces a simple spray of particles on the second screen behind it. So far so good. This result is actually consistent with both waves and particles. This is where things start getting strange. When shooting quantum particles at a screen with two slits in it, one would expect to get two sprays of particles on the second screen like what you get with classical particles such as bullets. However, when one actually shoots quantum particles at a screen with two slits in it, like a wave, quantum particles form a series of several light and dark strips as shown here. This shows the wave nature of quantum particles. One possibility that was considered is that quantum particles are somehow interacting to form the series of light and dark strips. The solution was to shoot the particles one at a time so that they cannot interact. When this is done, you still get an interference pattern. This is the case even with electrons. Note that the electrons still form an interference pattern, even when shot one at a time. This shows the wave nature of subatomic particles is inherent in each particle. These results actually seem to require each electron to go through both slits at the same time. However, this is not the end of quantum mechanical strangeness, because it gets even stranger. The notion that one particle could actually go through both slits at the same time is so anti-intuitive that physicists had to look to see which slit each particle actually went through. To look, experimenters put detectors by the slits so as to look to see which slit each particle actually went through. What they saw was a real mind blower. The result is that the subatomic particles formed a double slit line behind each of the slits, just like classical particles would, suggesting that the subatomic particles somehow knew when they were being watched and behaved differently because of it. This is not the end of this strangeness, because things are about to get even stranger. Suspecting the detectors were causing the different results, experimenters turned off the recorder while leaving the detectors on. This process also included the recorder being on, but not actually recording anything. To everyone's surprise, they got the interference pattern. The experimenters even had the recorder on, but the tape was removed while leaving the detectors on. They still got the interference pattern. The subatomic particles only produced the double lines when the information about them was actually being recorded. This was really strange indeed, because it could only be concluded that it was the act of measurement that affected the experiment and not the measuring devices themselves. All of this is part of particle-wave duality. This is the principle that particles exist as both particles and waves. The waves are not moving through a medium like sound or water waves, but they are waves of probability to where you will find a particle. The result is that every particle of matter has both a wave and particle nature. Here we have the formula for the de Broglie wavelength. We also expand it to include the effects of special relativity based on relativistic momentum. The relationship between the de Broglie wavelength and a particle's momentum is an important part of quantum mechanics, and it is a key to understanding how light works. It is also an important key to understanding quantum mechanics because it is one of the foundational principles of quantum theory. The uncertainty principle shows that there is a fundamental limit to the accuracy with which certain pairs of physical quantities of a particle can be known. A primary example of this is the position and momentum of a particle, which is why it is the primary representation of this principle. The wave function of a particle represents the behavior of that particle. It also provides the probability of where you will find that particle. For a free particle, the wave function is in the form of a plane wave. Here is the time-independent Schrödinger equation. It represents the rules that the wave function of a particle must obey. This is the time-dependent Schrödinger equation. It represents the rules that a wave function must obey over time. Combined, these formulas are the foundations of quantum mechanics. Don't worry if you do not understand Schrödinger's equations. That level of understanding is not necessary for you to understand what follows. Quantum field theory says that there are certain basic fields that occupy every point in space-time, and they are what make up the world. Furthermore, particles are excitations in these fields, making up what is called the standard model. These fields interact with each other, resulting in the phenomenon that we observe, including the matter that makes up our own bodies. This leads to an interesting question, and that is, what exactly is a field? In physics, a field is a physical quantity represented by a number or tensor that has a value for each point in space and time. In short, these fields are purely mathematical objects, not some kind of physical substance. For example, the temperature field of a room. What all this seems to show is that the particles that make up everything we know represent particular values in purely mathematical objects. This raises some interesting questions about the nature of reality. Since numbers and tensors are primarily types of information, it suggests that our reality is fundamentally information. Which-way path experiments are variations of the double-slit experiment that test different aspects of what was originally discovered by the double-slit experiment. These experiments explore different ways of detecting which-way path information, quantum behavior of different particles, and different types of which-way paths. They all share the same pattern. When which-way path information is knowable, there is no interference. When it is unknowable, there is interference. The goal of these experiments is often to probe the limits of this type of quantum behavior. The delayed quantum erasure is a variation of the double-slit experiment that shows that the change from an interference pattern to two spots is not a result of interference from a detector, but from whether or not which-way path information is known or potentially knowable about the particle. Furthermore, whether or not which-way path information will be detected is determined 8 nanoseconds after the signal photon has already been detected. The basic setup sends laser light through a double slit, one photon at a time, with a BBO crystal to split the incident photon into two entangled photons. One of which is called the signal photon, goes to detector 0, and the other, called the idler photon, is detected by detector 1, 2, or 3, 8 nanoseconds later. In the actual experiment, detector 4 was not used, but it is part of the basic setup. In this illustration of the delayed quantum erasure experiment, S is the light source, A and B are the two slits, and the BBO crystal is yellow behind it. D0 is the detector of the signal photon. BSA, BSB, and BSC are beam splitters. MA and MB are mirrors, and DO1, DO2, DO3, and DO4 are detectors for the idler photon. When the idler photon reaches BSA or BSB, half gets reflected to DO3 or DO4, respectively. The other half is transmitted and goes to BSC, where it gets reflected or transmitted to DO1 or DO2. If a photon is detected by DO1 or DO2, it could have come from either slit. As such, they provide no which-way path data, and in the experiment they produce an interference pattern. If a photon is detected at DO3, it could only have come from slit A. As such, it provides which-way path data, and in the experiment it did not produce an interference pattern, but produced a spot behind the slit, as seen in the classical double-slit experiment. If a photon is detected at DO4, it could only have come from slit B. As such, it provides which-way path data, and it would not produce an interference pattern, but would produce a spot behind the slit. Here is the actual data. As you can see, D1 and D2 produce interference patterns, while D3 does not. This occurs because D3 provides which-way path information, while D1 and D2 do not. Keep in mind that all three of these, D1, D2, and D3, are detected after the signal photon is detected at D0. These results show that the change in the pattern of particles does not result from the detector disturbing the particle, since there is no detector at the slit. This fact is enhanced by the fact that the signal photon is detected before the idler photon. The only variable in the results is the fact that DO3 and DO4 contain which-way path data, and D1 and D2 contain no which-way path data. This means that the existence of information about which slit the particle came through, or lack thereof, is what determines whether it behaves like a particle or a wave. Quantum erasure with atoms. The Mark-Zinder interferometer is designed to measure phase shifts in a beam split from one source. It has also been used in which-way path experiments using a single excited atom to detect which-way path information. In this experiment, because paths A and B have the same length, quantum interference produces a probability of 1 of the atom being detected at dx and a probability of 0 of it being detected at dy. This differs from the classical prediction of probabilities of 1/2 for the atom being detected by each dx and dy. In the Mark-Zinder interferometer, S is the source of the atoms, BS1 is a beam splitter that separates paths A and B, MA and MB are mirrors along the path A and B, BS2 is a beam splitter that combines paths A and B, dx and dy are detectors. Now, if a single excited atom is passed through a Mark-Zinder interferometer with non-destructive detectors dA and dB, causing the excited atom to drop to the ground state by emitting a photon, the resulting which-way path information destroys the quantum interference, resulting in the classical probabilities of half the atoms being detected at each dx and dy. Here we have the which-way path Mark-Zinder interferometer, with S as the source of the atoms, BS1 is as a beam splitter that separates paths A and B, MA and MB mirrors along paths A and B, BS is a beam splitter that recombines paths A and B, and dx and dy are detectors. dA and dB are the non-destructive detectors that detect which-way path information by causing an excited atom to drop to the ground state. Finally, if a channel is left open in both dA and dB that allow for the possibility of the photon being absorbed by an auxiliary atom, then the quantum interference is restored for these atoms where the photon is absorbed by an auxiliary atom. This shows that the which-way path information affects the behavior of more than just subatomic particles like photons and electrons, but for atoms as well. This further shows that what we know or potentially can know about these particles affects their behavior. In this illustration of the quantum erasure marked Zander interferometer, S is the source of the atoms, Bs is a beam splitter that separates path A and path B, Ma and Mb are mirrors along paths A and B, Bs2 is a beam splitter that recombines paths A and B, and Dx and Dy are the detectors. dA and dB are non-destructive detectors that detect which-way path information by causing an excited atom to drop to the ground state. C is an open channel that produces a probability of the emitted photon being absorbed by an auxiliary atom. Epsilon is the auxiliary atom that absorbs the photon. As with subatomic particles, when the which-way path information is known or knowable, the atoms behave classically. But when the which-way path information cannot be known, they act like a wave and produce the expected interference pattern. This delayed choice experiment uses a marked Zander interferometer where the beam splitters are substituted by optical Bragg pulses, BSP1, BSP2. The mirrors are substituted by optical pulses labeled MPA and MPB that send a single atom through the interferometer. In this delayed choice marked Zander interferometer, S is the source of the atoms, BSP1 is an optical Bragg pulse beam splitter that separates paths A and B. MPA and MPB are optical pulse reflectors along the paths of A and B. BSP2 is an optical Bragg pulse beam splitter that recombines paths A and B. Dx and Dy are detectors. After the mirror pulse was triggered, a quantum random number generator was used in determining if the last beam splitter pulse, BSP2, would be triggered or not. As a result, the atom cannot tell how it is going to be detected when it leaves the first beam splitting pulse, BSP1. That is, when the atom leaves BSP1, there is no indication as to whether or not BSP2 will be triggered. In fact, that is not determined until the last leg of the interferometer. Despite this fact, the atoms behave like waves when BSP2 was triggered and like particles when it was not. What this shows is that the behavior of atoms as well as subatomic particles is only determined when they are observed. Furthermore, the behavior is based on the information available about the atoms or particles. Here is a quantum erasure with a causally disconnected choice. In the main lab, the source splits the original photon into two entangled pairs with opposite polarization. The signal photon is then split by a polarization beam splitter, PBS1, that determines the direction the photon is sent based on its polarization. It then uses a marked Zander interferometer to send the signal photons along different paths that are recombined by BS before going to either detector 1 or detector 2. In a second lab, the idler photon is detected by another polarization beam splitter, PBS2. However, in a third lab, there is a quantum random number generator that sends a signal as to whether or not to turn on or off EOM, which can scramble the polarization of the idler photon. When the polarization of the idler photon is left alone, it provides which-way path information about the signal photon. But when the polarization of the idler photon is scrambled, that which-way path information is erased. Here's another case of quantum erasure with a causally disconnected choice. In this case, the distance is 144 kilometers. Not only does this separate the signal and idler photons in terms of distance, but it also separates them more in terms of time, thereby allowing a significant time delay between the detection of the signal and idler photons. As before, when the which-way path information is not known, you get the expected interference pattern, as seen on top. But when the which-way path information is known, as it is on the bottom, you get the photons detected at both detectors without any interference. You have two different sets of what are called Planck units. You have Planck's original units and those that are commonly found in textbooks. They differ by the factor of the square root of 2 pi, which is the factor that differentiates Planck's constant from the reduced Planck's constant. Planck's original units use Planck's constant, while the units found in textbooks use the reduced Planck's constant. Here we have Planck length, Planck time, Planck mass, Planck temperature, and Planck charge. One thing that using these units does is it reduces the fundamental constants, such as the speed of light, the gravitational constant, Planck's constant, the permeability and permeability of free space, all down to a value of 1, effectively eliminating these fundamental constants. You also have the derived units of Planck area, Planck volume, Planck momentum, Planck energy, Planck force, Planck density, Planck acceleration, and Planck frequency. The energy of the mass unit needs to fit the energy of a photon with a wavelength equal to the length unit. This means if you do the math, L has to equal h over mc, or length has to equal Planck's constant over mass times the speed of light. When we do the necessary math from the units, we get what you see here. This brings us to the wavelength of a photon with the energy of Planck mass equaling Planck length. The smallest possible black hole would have an energy level whose wavelength for a photon is twice the Schwarzschild radius. That is, that the wavelength would be equal to the diameter of the black hole. This results in the formula that we see here. This means that these two conditions must be met for true natural units, that being that 4gm over c squared equals h over mc. Following the math leads us to the mass of this smallest possible black hole. It leads to a mass that is 1/2 quantum mass, and it leads to a Schwarzschild radius equal to Planck's length. This means that these are natural units for measuring important physical quantities. The fact that this is possible is an important part of an information-based universe. It is also expected if the universe is a result of an intelligent programmer, such as God. What all these experiments show is that particles only have definite properties when information exists about those properties. Not only does this make the universe fundamentally indeterminate, but immaterial as well. This totally destroys the notions of determinism and materialism. Furthermore, it shows that there is a place in physics for God to work. It is fully consistent with God creating the universe by speaking, that is, imparting information. The Bible even gives a hint that the universe is fundamentally information. Hebrews 11:3. Through faith we understand that the worlds were framed by the word of God, so that things which are seen are not made of things that do appear. The result is that quantum mechanics devastates both determinism and materialism. The results of various which-way path experiments involving quantum particles show that they do not have definite properties unless the information about this property exists. This shows that the universe is fundamentally information. This clearly shows God's hand in the running of the universe. It is consistent with God creating the universe by speaking it into existence. It is also consistent with God running the universe at the fundamental level.